Hello, this is the third in a series of screencasts about reaction dynamics for the module 30042. And in this one, we're going to talk about a little bit more about collision theory, and in particular about how it applies, and whether it's any good, really. Okay. The reading for this is exactly the same as it was for the second screencast, and once again, I've got some page numbers and also some QR codes here that you can follow if you find that useful. Okay. So just to recap, collision theory basically assumes that reactant species are hard spheres, and once again, a hard sphere is something that has an infinite repulsion once you get to the radius of that sphere, but outside of that radius of that sphere, so spheres here and anywhere outside the radius of that sphere, there's no interaction whatsoever. Okay, so get to the radius, infinite repulsion, so things just bounce off it. Anywhere away from that, then you have no interaction. Okay, so taking that assumption into account, it means that you're ignoring any sort of the interactions that honestly we usually require in chemistry for reactions to actually work. So you can already think that this is going to be a bit of an approximation. The other thing that hard spheres assume is that you don't lose any shape or size on the collision, and that kind of makes sense because they're hard. Yeah. The second assumption that collision theory makes is that you need a collision to occur, and as I said already, that collision is sometimes caused by the mechanism, and we're going to talk about how that alters the collision theory equation today. Okay, and the final part of the theory is basically that the colliding molecules have to have enough energy to react, so that's where the sort of that fraction of successful collisions part of the equation comes in. Okay, so here is the collision theory equation, and so once again you've got quite a horrible looking equation, but we did explain where all of these different pieces again, and just to recap, this is where all the pieces come from. So this Euler's number to the half, this is the bit that allows our activation energy in this exponential term here to be the same as the activation energy in the Arrhenius equation. This here is the part that takes into account the size of the molecules. So this is the collision area. So this is the idea of a molecule moving through a forest of other molecules, and this is given by the radius of the two species added together, squared and multiplied by pi to give us the area. Okay. This part here is accounting for the speed of the two species that are colliding with each other. This L is Avogadro's number, so just remember that it's capital L in these lecture notes, not the usual NA. And finally, this part here is accounting for the fraction of successful collisions. Okay. So how well does collision theory work? And so one thing I should probably note is that I frequently do abbreviate collision theory to CT. Okay, so just whenever you see capital C, capital T, that means collision theory. So generally speaking, though, collision theory provides actually quite a decent approximation when you have simpler reactions. And by simpler reactions, I mean these kind of reactions here that we've highlighted. So I'm just going to get the pointer up actually. These reactions here. So you've got a species like bromine. And the atom of bromine is probably fairly well represented by a sphere, okay? And hydrogen, whilst it's not spherical, it's not going to be too far from a sphere. So again, this is going to be relatively well represented by a sphere, and hydrogen's a pretty simple molecule, so saying it's a hard sphere is not too much of a jump. And so as you can see here, this is the comparison of the collision theory calculation. So this is these numbers here, A calc. Okay, so this is the calculated pre-exponential factor. So this is everything apart from that exponential bit. Okay, and these are the observed values. So these are the experimental values. And you can see that in both these two reactions that I've got in this green box here, these values are not too far apart. They're not exactly the same, but they're similar. And one key point to note is that they're similar, but generally speaking, collision theory is overestimating the pre-exponential factor, and therefore will overestimate the rate. But it's not a bad approximation in these cases. However, when we look at these two cases down here, you can see that in these two cases, and particularly in this one here, the difference between collision theory calculation and the observed rate is significant. Okay, so why is this? Well, in this reaction, I've got an example of it down here. This reaction is going to require a very specific direction of approach and a very specific molecular orientation. in order for it to work. Yeah, in order for the orbital to overlap in the correct manner that you know through your organic chemistry learning, and so that the reaction can actually work correctly. Okay, so you know this already, but that is why collision theory is doing a bad job of approximating the rate, because collision theory is just saying, well, any direction of approach, any molecular orientation, that's all going to be fine, because collision theory assumes the reactants are spheres, and for spheres it doesn't matter which way they come from, they're going to bash together the same no matter what. Yeah, whereas we know our reactants, and particularly in these cases, they have a shape, and you need a particular direction of approach. So this is the limitation of collision theory in this case, and it's why collision theory vastly overestimates the rate, because the reality is that only a very small percentage of the reactions coming from different directions are actually going to work, because only a small percentage are going to be in the correct direction. This one down here is a bit different, and I will talk about this on a later slide. This one here has a very specific mechanism, and it's an unusual case where actually the observed rate is bigger than that of collision theory, that calculated by collision theory. And this here has a specific mechanism, and it's called the harpoon mechanism. I will talk about that later on. So we can introduce a factor that can account for the difference between the calculated value and the observed value of the pre-exponential factor, which is obviously going to be related to the calculated and observed values of the rate in the same way. Okay, and this steric factor, or P, then allows collision theory to give the same result as experiment. Okay, so basically the way we calculate P is we say P is equal to the observed value for the pre-exponential factor divided by the calculated value for the pre-exponential factor. Equally, you could say it's the observed rate divided by the calculated value of the rate, or the observed rate constant divided by the calculated value of the rate constant. Or actually, you can also say that it's the observed collision cross-section divided by the calculated collision cross-section. And the reason for this is because every other parameter in the equation for collision theory is well known. Okay, so we know the masses of our reactants, we know all the constants, we know the activation energy, because that's the experimental activation energy. So everything else is well known. The only thing that isn't well known is the collision cross-sectional area. Okay, and so P is often expressed as a ratio of the cross-sectional areas. Okay, so this is the thing that collision theory gets wrong, basically, and the reason it gets that wrong is because of these orientations, directions of approach, etc. Okay, but this is how you can calculate P, and so we calculated P in the table down here, and you can see when P is sort of getting close to 1, that's obviously a good agreement between collision theory and experiment, whereas when P is quite far from 1, then you're going to get a poorer agreement. And it's worth noting that generally speaking, these three values in the top 3 rows of the table, they're pretty common. It's commonly the case for bimolecular reactions that collision theory will provide a value of P between 0 and 1, and that the approximation of the rate is going to be better for simpler reactions, as we already said in the previous slide. The one down the bottom here that I've put in a box, as I said already, in this case, P is bigger than 1, and this implies that basically the observed cross-sectional area is bigger than the one we've calculated. So it's bigger than the one that we assume by, say, for example, the van der Waals radius. So this has to have a specific reason for it, and that's the reason I'm going to go to the next slide. So the specific mechanism that explains the reason for why the reaction between potassium and bromine, Br2, the collision cross-section is bigger than predicted, is known as the harpoon mechanism. And it just requires you to remember something about potassium and something about bromine. Bromine really wants to pick up an electron, potassium really wants to give it away, and so what happens is potassium will essentially harpoon the bromine molecule, and that's where this sort of word harpoon comes from. And so what happens is an electron jumps from the potassium atom towards the bromine, leading to the creation of 2 charged species, and these charged species will then attract one another. And obviously, you know, we put in this harpoon here, which is, you know, not physical, but nevertheless, it's the same idea. You now have an attractive interaction between the two species, and that will pull them together, and that's what means that the collision will then occur. So the effective collision area is made bigger by this, because the effective collision area is the radius of the two species, the effective radius of the bromine, the radius of the potassium, plus the distance that this electron can jump. Okay, and obviously once they collide, they can result in the products. Just as a sort of slight aside, we'll talk a bit more about the sort of experiments that can be done to look at these reaction mechanisms. But the harpoon mechanism was determined through one of these sort of advanced experiments, which cross the molecular beam, which is where you basically control the direction of two molecular beams, and you see how that, you know, influences the products. You measure the products that come off, and you can also measure other properties of those products too, such as the sort of IR of those products to tell what bonds are being broken and formed, that kind of thing. Okay. The key here is, of course, the presence of these long-range attractive forces. Okay. Obviously, collision theory is assuming hard spheres, doesn't allow for those long-range attractive forces. So, you know, this mechanism is why P is different to 1. Okay, so just to summarize collision theory, I've once again put up the equation here, but now I've included this P, this steric factor, which now brings the calculation of K2 into agreement with experiment. Okay, so collision theory is good because it emphasizes the importance of collisions. Okay, and that's great, because that means we already have something, we have a handle on something that has to happen for a reaction to occur. The other good thing about collision theory that you may have already noted is that the pre-exponential factor, so the bit before the exponential, is now temperature dependent, which will start to account for those curved Arrhenius plots that I introduced in the first video for this course. Okay, so this starts to bring that idea in. And so the temperature dependence of K in this case is T to the half multiplied by the exponential of, it should be a -1 here, -1 over T. Okay. Of course, you know, that's two good things, but, you know, collision theory is very simple. Okay, and there are clear issues with it in the fact that it doesn't even correctly predict the rate for even the simplest reaction that I had in that previous table. And we've already explained something of why this is. For example, we've said that the approach direction is not taken into account, orientation is not taken into account, and these definitely apply in more complicated scenarios. The other issues are that, you know, you're only taking into account the mass through this part here and the size of the molecules. And to be honest, even that size of the molecules, you have to rely on using a van der Waals radius, which might not be quite true in all cases. And certainly, you know, in the case of those specific mechanisms, the harpoon mechanism, that's wrong. You know, you're not taking into account the internal energy that the molecule possesses and where it is, and you're not taking into account any intermolecular interactions. So this is all coming back to the idea that collision theory assumes that the species are hard spheres and that most chemicals, most reacting species aren't. Okay, so that's really the problem. And finally, you know, the problem with this equation up here, which includes P, and that obviously, you know, when it includes P, you can get the correct answer, you can get the right answer, but the problem is we haven't got a clue what P is. Okay, so if we haven't already measured the reaction and done the calculation and figured out what P is, we can't do any predictions. So in that case, actually having the whole equation with P in it is kind of not very useful. All right, so we can't predict P, and therefore collision theory falls down on that case. Okay, the final part of this recording concerns an exam style question on collision theory. And so this is the sort of thing that might turn up either in the problem sheet or could turn up in the final open book assessment. Okay, so obviously you can read the question. We're given an experimentally observed Arrhenius pre-exponential factor. So that's this, and this would be the same as A observed. Okay, and we've given a reaction and we're given a temperature. Okay, it says here that we've essentially got to calculate collision theory equation on the basis of this information that we're given. Okay, so we've got the two molecular diameters, So that's a key point of our species, and we're also given the species. And so we've got to first find our A calc, yeah, and then we've got to find P. And so there's a few key points here. One is that these species are obviously diameters. The other thing is that they need to be converted into meters. So for example, they need to be converted from diameters to radii, and they need to be converted from nanometers to meters. And also we're going to need the masses of these two species too. Okay, so we're going to need to go and find those. And obviously one of those resources, you know, you can use the periodic tables that are at the back of any of your lab scripts that you used to have. Okay. On the next slide, we're going to go through this. Okay, so the first thing I'm going to note is the masses of the chlorine and the hydrogen. So mass of 35 Cl is 34.97 grams per mole. Yep. Apologies for the elongation of that. I'll probably I'll just erase that one and get back to it in a minute. There we go. Just 97 grams per mole, and the mass of the hydrogen is 2.016 grams per mole. Okay, you know, and so you can get these values, like I said already, you can get these values either online, or you can try to use the back of your lab diaries. I think in this case you need to find it online, whereas for the hydrogen you can figure it out. I would say you could, of course, use 35 here and 2 here, but the problem with using 2 for the mass of hydrogen is that you limit your final answer to one significant figure, don't you? So we probably need to be a little bit more accurate than that. Right. Anyway, from that, we can calculate the reduced mass because that's the first parameter we're going to have to get. Okay, so the reduced mass is going to be equal to the mass of this multiplied by the mass of this divided by the 2 added together. So, and we're going to stick in grams per mole for now, just because that's a bit easier to do, I think. So I'd recommend this way round. Times by 2.016 grams per mole, all divided by 34.97 plus 2.016 grams per mole, because when you add the two together you get the same units, don't you? And of course these cancel, so we get an eventual unit of grams per mole for our reduced mass, which makes sense. And the answer to that is 1.9061 ... grams per mole. Now this ... this implies basically that I've kept the number in my calculator with more significant figures than I've written down on this paper here. I mean, you could just write all of the significant figures down. The point there is that you really want to keep these as full values with all their sig figs until the very end, and we only round up at the very end. Okay. Now this reduced mass is fine, but this needs to be in kilograms. So we need this in kilograms per molecule. Okay, so we need to convert this from grams per mole into kilograms per molecule, and we do that by first converting the grams to kilograms and then dividing by Avogadro's number to get rid of the per molar. So we say mu is equal to 1.9061. Now 1 gram is equal to 10 to the minus 3 kilograms, isn't it? So we can just substitute 10 to the minus 3 kilograms in place of grams. So we say kilograms, oh, wait a minute, done that wrong, haven't I? So do that again, 1 times 10 to the minus 3 kilograms per mole divided by Avogadro's number, which is 6.022. I put a ... in again because you can of course get more decimal places for that. Times by 10 to the 23 per mole, and we can see that the per mole is cancelled to give us an answer in kilograms, and that is equal to 3.165 ... times 10 to the minus 27 kilograms. Okay, so important thing to note about this is that 10 to the minus 27, 10 to the minus 26, these are values that are pretty common for that reduced mass. Okay, So if you get those if you get that sort of value, then you've done your calculation right. And so that's the first step. The next step we need to do is to calculate the collision cross section. Okay, so for that we need to sort of note the diameters of our chlorine and our hydrogen, and we need to basically convert those to radii first and foremost. So I'll just make notes of those. So so for 35C, D is equal to 0.36 nanometers, whereas for our 2H, sorry, H2 even, what am I on about? 2H, that's deuterium. D is equal to 0.24 nanometers. Okay, so that one's pretty similar to the one I had in a exercise for you. Okay, so we need to therefore find the radii, and so that's simply by dividing by 2, and I think I can cope with that in my head. So that's 0.18 nanometers in this case, and in this case it's 0.12 nanometers. Now obviously 1 nanometer is equal to 10 to the minus 9 meters, and so we can sort of put those into here and you know, substitute in 10 to the minus 9 meters in place of nanometers in both cases, but we'll do that in a minute. All right, so in order to calculate first the collision cross section, we first need to find the collision diameter. So I'll do that. So this will be collision diameter, and that's equal to the 2 radii added together. So that's basically going to be 0.18 nanometers plus 0.12 nanometers, which is, this is not so difficult, is it? So it's 0.30 nanometers, which is the same as writing 0.3 times 10 to the minus 9. I've just lost myself some accuracy, so 0.30 times 10 to the minus 9 meters, or we can write that as 3 even, 3.0 times 10 to the minus 10 meters, can't we? Okay, so then we need to find the collision cross-sectional area, and that's equal to pi times by the collision diameter squared. So that's pi times by 3.0 times 10 to the minus 10 meters squared, and that gives us 2.83 again, times by 10 to the minus 19 meters squared. Okay, once again the ... implies that I've kept the accuracy. I've only written down 3 sig figs, but I've kept more in my calculator. Okay, so putting it all together, we've got our values for our reduced mass. So reduced mass is equal to 3.165 ... times by 10 to the minus 27 kilograms, and we've got our collision cross-sectional area, thermojig AB, calculated obviously, and that's going to be 2.83 ... times by 10 to the minus 19. And again, as with as I said for the reduced mass, you know, 10 to the minus 19, 10 to the minus 20 maybe, 10 to the minus 18 maybe. These are orders of magnitude that are sensible for our collision cross section if expressed in meters squared. So, you know, if you haven't got those order of magnitude, chances are you've made a mistake in the conversion at some point in time. Or you've just used a diameter instead of a radius, maybe too. Okay, so we've got these two things. We can then basically put them into our equation. So our calculated value for A is given by Euler's number to the half times by this here, this collision cross-sectional area, times by 8 kBT over pi times by mu, and that is square rooted, and that's a really key point because this is something that sometimes people forget to do, and that's times by Avogadro's constant. Okay, so that's the equation we're going to use. We're going to put these numbers into it. I'm not going to explicitly write this out because, you know, obviously you would probably just do this on a calculator, but if you do write this all out and if you do go through this process, what you will end up with is a number along the lines of 5.14 ... times by 10 to the 8 meters cubed per mole per second. Okay, and this is a key point. This equation, when you use it as it is with all these SI units, and you can prove this to yourselves by, you know, following the unit tracking through, this equation is going to give you the values in meters cubed. Okay, so you must remember that, and you must then adapt that, you know, to decimeters cubed, so we can put it in per molar per second, right? So we can rewrite that out. If we've still got this, we've got our ... So this is an inappropriate level of accuracy. The thing that's going to hold our accuracy was those initial values of the molecular diameters, and they were given to 2 sig fig max. So we've got 2 sig fig max due to diameters. And so therefore we've got 5.1 times 10 to the 8 meters cubed per mole per second, and that's the same as 5.1 times 10 to the 11 decimeters cubed per mole per second, or same as per molar per second. Yeah. Okay, so I need you to be able to know how to do that conversion and get it right. Okay, and finally, to finish off the question, it asked us to calculate P as well. Well, in order to calculate P, we basically say P is equal to A calc divide, sorry, wrong way around. A observed divided by A calc, and that is equal to, from the question, 8.48 times 10 to the 10 per molar per second divided by 5.14 ... times 10 to the 11 per molar per second, and that is equal to 0.17. Now, key point here again, I used the value with the full number of full accuracy in doing this calculation, so just don't forget that when you're doing calculations, keep the accuracy in, but at the end I have again rounded it up to 2 significant figures because that's the appropriate one, judging by the number of appropriate significant figures for A calc in the first place. Okay, so I need you to be able to do this kind of question. So one of the things I'll be getting you to do as part of the associated exercise with this screencast is to follow through a similar example yourself and check that you can also do the same calculation. Okay, thanks for listening.